This is section 8.1b, Introduction to Matrices. Today we're going to talk about Gauss-Jordan Elimination. Now, let's back up a tiny bit and first review Gaussian elimination. We know that the goal of Gaussian elimination is a matrix in row echelon form, such as this matrix. This is a typical matrix in row echelon form. We have zeros in the bottom left portion of the matrix. We have ones on the diagonals and other constants in the remaining portion of the matrix. And we've been doing this a lot, so there's no need to talk a lot about row echelon form. But just to review that the basic objective when we do Gaussian elimination is to end up with a matrix like this. And of course, once we get it in row echelon form, it's very easy to find the values of each variable. So what is Gauss-Jordan elimination? All right, well, Gauss-Jordan elimination simply takes Gaussian elimination a few steps further, because the goal of Gauss-Jordan elimination is a matrix in reduced row echelon form, such as this matrix. All right, so this matrix is in what we call reduced row echelon form. So the coefficient portion of the matrix, right, the first three columns, as you can see, has a very simple pattern: ones on the diagonal and zeros everywhere else. Now, the reduced row echelon form is actually a little bit easier. Obviously, we need a few more steps to get to it, because we have to make more positions zero than we do with normal Gaussian elimination. But once we do those extra steps and we end up with a reduced row echelon form matrix, we can read the answers directly off of the matrix. Okay, so for example, if this matrix represents a system of three variables and three equations, x, y, z, well then z equals 2, y equals -1, x equals 1. All right, so we can see that we, with Gauss-Jordan elimination, we end up with a very easy solution at the end that we can read directly off of the reduced row echelon form matrix. Now we'll go through a specific example of Gauss-Jordan elimination. Write the following system as a matrix and solve by Gauss-Jordan elimination. Our matrix is x minus 2y plus 3z equals 9, negative x plus 3y equals -4, 2x minus 5y plus 5z equals 17. Writing this as a matrix, it's pretty simple. 1, -2, 3, 9, -1, 3, 0, -4, 2, -5, 5, 17. Okay, so we have our system. We've written it as a matrix, and now we want to perform Gauss-Jordan elimination. Well, as you can imagine, the first few steps of Gauss-Jordan elimination coincide with Gaussian elimination, because before you can get to reduced row echelon form, you have to first get to row echelon form. So what I'd like you to do now is perform the necessary row operations to get this matrix into row echelon form. You should pause and then resume when you have the row echelon form. And then, once you have the row echelon form, we're going to go through the steps together of how to carry it further to reduced row echelon form. Okay, so pause now, get row echelon form, and then resume. All right, now we're going to just quickly go through the steps that you should have followed in order to get row echelon form. The first step is to simply add row 1 to row 2. And when you add row 1 to row 2, you get 1, -2, 3, 9, 0, 1, 3, 5, 2, -5, 5, 17. All right, the next thing we want to do, because we want to get rid of that 2 in the lower left corner, is first we are going to multiply the first row by -2. We get -2, 4, -6, -18, 0, 1, 3, 5, 2, -5, 5, 17. Now I can add row 1 to row 3, and I'll end up with -2, 4, -6, -18, 0, 1, 3, 5, 0, -1, -1, -1. All right, getting closer to row echelon form. And now I can simply add row 2 to row 3, and that'll eliminate the y coefficient in the third row. And I end up with this matrix. This is the matrix that I end up with. -2, 4, -6, -18, 0, 1, 3, 5, 0, 0, 2, 4. And the final step to get row echelon form is to multiply each row by appropriate constants. And when I do that, I multiply row 1 by -1/2, I get 1, -2, 3, 9. Row 2 I leave alone, and then row 3 I multiply by 1/2, and I get 0, 0, 1, 2. So I now have my row echelon form, All right, at this point I'm going to walk you through the steps to continue now onto reduced row echelon form. And so up until this point, it's all been Gaussian elimination. Once we proceed with the following steps, we are going to be doing Gauss-Jordan elimination. All right, so my next step is I'm going to multiply row 3 by -3. I get 1, -2, 3, 9, 0, 1, 3, 5, 0, 0, -3, -6. Then I simply add row 3 to row 2, and I get 1, -2, 3, 9, 0, 1, 0, -1, 0, 0, -3, -6. And then, conveniently, I can also, at this point now, add row 3 to row 1, because that's going to get rid of the 3 in the first row. And when I add row 3 to row 1, I get 1, -2, 0, 3, 0, 1, 0, -1, 0, 0, -3, -6. We're getting closer to reduced row echelon form. Now, I still have to get rid of that -2 up there in the first row. So what I'd like to do now is simply multiply row 2 by 2, and I end up with 1, -2, 0, 3, 0, 2, 0, -2, 0, 0, -3, -6. At this point, you can clearly see that we can add row 2 to row 1, and I'll end up with this matrix: 1, 0, 0, 1, 0, 2, 0, -2, 0, 0, -3, -6. Almost there. We're almost at reduced row echelon form. The very last step is to get 1s in that diagonal, and to do that I multiply each row by the appropriate constants, and this is what I end up with. Row 1 stays the same, row 2 gets multiplied by 1/2, and row 3 gets multiplied by -1/3. And so I end up with this reduced row echelon form matrix: 1, 0, 0, 1, 0, 1, 0, -1, 0, 0, 1, 2. And I can conveniently read the values for the variables straight off of the matrix. So z equals 2, y equals -1, x equals 1. And going to the first row, I get my x equals 1. Going to the second row, I get my y equals -1. And the third row, z equals 2. Okay, so it is a little bit more work to do Gauss-Jordan elimination, but it's easier once you get to the final step. But the main reason we're learning Gauss-Jordan elimination is because this is what calculators do. And from this point on in the course, you are going to be able to use your graphing calculator for matrix operations. You'll find that it's not only faster, but also more accurate. It will eliminate those small arithmetic errors that are so easy to make when you have many steps and you're doing these steps by hand. Okay, so now is the time to consult your manuals or consult a senior who already has taken this course and is a master of his or her calculator. And learn how to first create a matrix on your calculator, and then to perform row reduction. Okay, we're going to use the same exact system and the same exact corresponding matrix. And every calculator is different, but one thing that most have in common is once you do have the matrix entered, so you have to learn how to do that on your own. You should look for a row reduce button or function. Sometimes it's called RREF, which stands for Reduced Row Echelon Form, RREF. These are the buttons or functions that your particular calculator might use. So, but you have to, that's your responsibility, to learn how to use your own calculator. So what you want to do now is pause the video, figure out how to do this on your calculator, to create the matrix, and then to row reduce or RREF on your calculator in order to produce the row reduced echelon form. Resume the video when you have that done. And so your calculator should have given you this. This is exactly what we came up with by, when we did it by hand. But it's obviously much faster and more accurate on your calculator. So 1001, 010, -1, 0012. Please make sure that you know how to use your calculator for matrices before coming to the next class. Here's the classwork, page 584. Please write these numbers down. Note that the ABC there on number 89 just means you're only going to do ABC, not the other letters. And the same is true for 90.